Now the word normal, the unit, all this we're dealing with unit, okay, unit, normal, vector. Okay, the word normal, as you may know, in terms of planes, in terms of lines, is simply a vector that is perpendicular to the curve. Well, that is what it exactly means over here, which is this vector over here. Okay, the curve is like that, the unit tangent vector is here, the unit normal vector is over here, perpendicular, or another term is called orthogonal. If I remember correctly, orthogonal basically it just means it's perpendicular to the unit tangent vector here, the normal. Okay, so now by looking at this, we might kind of think that, why is that the case? Why would this be the normal vector, and moreover it's gonna be the unit normal vector? Now I'm going to show it to you, because in maths, we always try to write the formula and then we still need to prove, we still need to show it. So we're dealing with two aspects, the unit aspect and the normal aspect. Okay, let's just handle the first one here. Unit, right, meaning is of length, unit length 1. So basically we take the modulus of this, we get the unit length 1. Let's do that and see what we get. Okay, let me just push the whiteboard a bit over there so you can see what I mean. I'll do it over here, okay. Taking the modulus of these two quantities, okay, rho and the differentiate of the unit tangent vector in terms of s, they modulus that. Okay, now rho by definition is 1 over k, so 1 over kappa, so we put 1 over kappa here, and then we also got here that if we take the magnitude of the differentiating the unit tangent vector in terms of s is kappa itself, hence equals to 1. There we go. By definition of these two, the length of this normal vector n in terms of s is 1. As I showed over here, take the magnitude, by definition 1 over kappa times kappa equals to 1. So we handled that part. The length we now know is the normal, is unit length of 1. So now the normal vector, now that's a bit trickier to show, but I believe with some help from the previous sections we can show that. Okay, now I don't expect you to really know how to do it, but because it's quite difficult, we're taking the tangent vector and we're differentiating it with respect to s, and we're finding the relationship between the two. But if you recall in the previous sections, there is this thing called the dot product. And by taking one of the properties of the dot product, which is a fairly important property, I hope that it goes with you a long way, is that if you dot a vector by itself, you will get the magnitude and you square that, such as this is what I mean. Okay, this is a property which I believe I've shown, or I will show in the previous sections, previous chapters, that if you dot a vector by itself, you get the unit length. Okay, that is fine. So let's just take it from here. The magnitude of t, well, what do we define t as? T is the unit tangent vector, right? As over here. Magnitude is equal to 1. Okay, that's the first step, because we got 1 over here. However, we got a t dot t over here. So now we will differentiate both sides with respect to s. Okay, with respect to s. Differentiate this with respect to s. Okay, properties of differentiating the dot product is similar to the product rule. We differentiate this dot by this, we keep this, and we dot by this, and we add the two together. So it's equal to this dot t, add up with t dot t, this one. Okay, and differentiate 1 as cos, you get 0 over here. Okay, so now by the commutative rule, we can inverse this too. So t dot t is the same, t dot t dash is the same as t dash dot t. So this is written as 2 t dash dot t equals to 0. Okay, and then we divide by 2, is equals to 0. However, what is t dash? Okay, t dash is differentiate t with respect to s, or simply written as this over here. Okay. And then that's what we define it as. This one, as you can see, is over here. So if we were to rearrange, differentiate t with respect to s is simply 1 over rho times the normal vector. So writing this whole thing out would be 1 over rho, the normal vector. I'm just simply rearranging this. I'm bringing rho over the other side so that I get this term by itself, so I can substitute inside here, which is over here. Okay, so yeah, I'm substituting this term over here and substituting it over here. So the normal vector dot by the unit tangent vector is equal to 0. Properties of the dot product: when two vectors dot each other and you get 0, they are mutually perpendicular, or they are orthogonal like we are trying to show over here. And that is why we can say that the vector n, or we define a vector n in terms of s, is equal to rho times differentiating the unit tangent vector once in terms of s. That will give us the unit normal vector, as we have shown over here. So quite a lot of terms, quite a lot of theory. Kappa, rho, curvature, amount of bending radius of curvature, unit normal vector, unit tangent vector, dot the two mutually perpendicular, a lot of concepts, but it's worthwhile to learn. Okay? Though just a main point, a key point in all this is that we are dealing with the arc length. Okay, just bear that in mind for the subsequent problems. Later we can convert this in terms of t using chain rule. But just bear in mind that in terms of kappa, rho, and the normal and the unit, the normal and the tangent, we are all putting it in terms of the arc length s. Okay, over here, over here, over here. And there you go, curvature. That's what it's all about.